All right, so let us carry on our discussion on the differential amplifiers. Okay. So far in the differential amplifiers, we had assumed that the tail current source, so that is this tail current source was ideal. Okay. But now let us assume that this tail current source is not ideal. That is, it is associated with a finite impedance. Okay. So we want to study the effect of finite tail impedance, okay, which can be associated with this current source, which is now in this case not ideal. And when it was ideal, then we had commented that for a small input signal change, this node P, that is potential at this node, so this does not changes. So we had assumed earlier, okay, that is delta Vp was 0 for a small change in input. So let us say the input changes by delta V on both the sides. So for this small change in the input voltage, this Vp was fixed. So this Vp does not change. So delta Vp was 0. So that was the case when this source was ideal. That is when it was associated with the infinite tail impedance. But now in this case, we have a finite tail impedance. So this source is not ideal. So Vp, delta Vp is not 0 in this case. Okay. So a change in input voltage, a small change in input voltage, let us say delta V. So this, let us say, causes the change in current in IC. Okay, that is, the collector current of Q1 and Q2 will see a change because of this small signal change at the input. Okay. So earlier when the case was that this source was ideal, we said that the current of these two transistors have no effect if the common mode input voltage varies. Okay. So it had no effect, that is that these two currents had no effect from the common mode input voltage, because these two currents were fixed by the tail current. But here, since now this case is not a non-ideal case where we have a finite tail impedance, so a small change in input signal will also cause a small change in the collector currents. So let us say those small changes in the collector currents are delta IC. Okay. So delta V small change in the input causes delta IC small change in the collector current, and Vp, that is delta Vp is not 0 now, that is you have change in potential at P point also, which is not 0 here. So in fact delta Vp can be written, okay, so delta Vp I can write by saying the current which is going into this multiplied by REE, and the current that is going into this tail impedance is delta IC from here, delta IC from here, that is 2 delta IC. So delta Vp would be 2 delta IC multiplied by REE. So 2 delta IC multiplied by the finite tail impedance. Okay. So I can write delta Vp as 2 delta IC times RE. Now similarly I can write the relationship between the base to emitter voltage. Okay, that is, this is my base over here, emitter is common, right? So I can write base to emitter voltage VBE. So VBE would be equal to here VBE1, let us say, so this would be equal to VB1 minus VE, okay, or VB1 minus VP, okay, and VB1, that is, this is base 1, VB1 is VCM, so I can write this as VCM minus VP. Okay, so this delta VBE for a change in input voltage delta VBE is also changes by delta VBE. Okay, so everywhere I'll put delta here, so which represents a small change because of small change in the common mode input voltage. Okay, So delta VBE1 is delta VCM minus delta VP. In fact, delta VBE2 also is same. Okay. So I can write delta VBE as delta VCM minus delta VP, or I can take this delta VP on the left hand side and I can write delta VCM is this much. Okay. Now VP we have already found here, so this VP I can put here in this equation, so this equation modifies to this equation. Okay. Now delta VBE, so I can write GM as delta IC by delta VBE. Okay. Small change in current divided by small change in the base to emitter voltage. Or from here I can write delta VBE as delta IC by GM. Okay. That is, this delta VBE I can write as delta IC by GM. And from here I can find out delta IC then. So delta IC is this much. Delta VCM by 1 by GM plus 2 REE. Okay. Now because of this change in collector current in both these two transistors, these output will also change. Okay. So they will not remain fixed, they will also change by some amount. Okay. So the change in the outputs, that is delta V out 1 and delta V out, can be written. So delta V out, that is change in output voltage 1, will be equal to change in current multiplied by RC. Okay. That is minus IC, delta IC RC. Similarly, delta V out can be written. Okay. That is change in the collector current multiplied by RC. Okay. And then from this one can find out this ratio, which is also the common mode gain of this circuit, okay, which is delta V out by delta V in, common mode. Okay. So this ratio can be found, okay, by knowing that delta V out CM is V out 1 minus V out 2, okay, and also knowing delta IC as this much. So if I use this equation, delta IC, and we also use delta V out common mode as delta V out 1 minus delta V out 2. Okay. And let us say that these two values, there is a little bit difference in these two values, otherwise this will be 0. Okay. So this little bit difference can only be present if these two resistances are not completely matched. Okay. So let us say it is this collector resistance does not matches this collector resistance RC, and let us say this is RC plus delta RC. Okay. So then one can find out a relationship between, that is this common mode gain, that is delta V out by delta V in. Okay. Delta V out minus V out 2 by delta V in common mode, which is 2 times delta VCM, right, or 2 delta V in this case. Okay. VCM is present here also and here also. Okay, so this will go off, so you will be left with this part, which is actually the gain of this circuit. Okay. Now earlier we had commented some time back that if a common mode input signal is applied, that is an input signal which is common to both these two transistors. Okay. Common, that means magnitude is also same and phase is also same. Then the differential output should be 0. Okay. But in this case the differential output is not 0. Okay. We want this value to be, that is this differential, this gain should be 0 in this case, but actually it is not 0, it is finite. Okay. Which is because of this non-ideality present in the current source. So because of non-ideality in the current source, you have finite tail impedance, and because of this finite tail impedance, your common mode gain is not exactly zero. Okay. So common mode gain we want to be zero, or we want this to be very small, or ideally zero. Okay. Now let us compare this with the case where my tail current is ideal. Okay. And let us say that the input is differential, V in 1 and V in 2, and to these two inputs a common mode signal is applied, that is, let us say this is some noise which is common to both inputs A and B, or inputs V in 1 and V in 2. Okay. So that means the inputs at A and B, so they are both corrupted by noise, this noise. Okay. Now the output 1 and output 2, the single-ended outputs, so they will be free from any noise. Okay. So this noise, common mode noise, so this gets cancelled, and in the single-ended outputs you do not see any noise. Similarly, in the differential output, that is Vout1 minus Vout2, we further see no noise. Okay. And if we compare this with the case when the current source was non-ideal, that is non-ideal tail current source was present because of finite impedance, and in this case also let us consider differential inputs at A and B, and a common mode signal or some noise is now present at both these two inputs. Now the effect of this noise signal present at A and B is that my single-ended outputs Vout1 and Vout2 are also corrupted by noise. Okay. So these are corrupted by noise. But the differential output, so this rejects this noise from the inputs and also any noise coming from the ripple from VCC. Okay. So that is differential output is clean here also. So clean differential output without any noise. Okay. So in the previous case also the differential output was clean without any noise. Okay. But in the previous case the single-ended outputs were also clear without noise. But here in this case the single-ended outputs are corrupted by noise. So one can compare the ideal tail current with non-ideal tail current. Yes. So just now we had made a comparison that if both the inputs are corrupted, then if it is an ideal tail current, the single-ended outputs are not corrupted and differential output is also not corrupted by noise. Similarly, for a non-ideal tail current, if both the inputs are corrupted by noise, the single-ended outputs are also corrupted by noise, but the differential output is free from any noise, that is, the differential pair is not affected by a small input common noise. Okay. So for small input common mode noise, this differential pair is not affected, output is not affected. Okay. Now in the previous circuit, as I said that I need to also assume that these two collector resistances, that is RC, so they are different. Okay. So that is for this small change in VCM, my collector current, this collector resistance, so this also sees a change, that is this collector resistance is, let us say, RC plus delta RC. Okay. So otherwise the differential output will be 0. Okay. So but we want to incorporate the effect of this finite input impedance And for finding out the effect, I assume that the input signal changes by delta VCM, okay, which causes a change in the collector currents Q1 and Q2 by delta IC amount. Okay. So VGS can be written as VCM minus VP. VP is 2 delta IC R double E, right? So delta IC plus delta IC flowing in REE, tail impedance. So VP, that is delta VP. So this is not 0. So delta VP is this much, 2 delta IC REE. So I can write delta VCM as VBE plus 2 delta IC RE. Then VBE can be written as delta IC by GM. Okay. And from here I can find out delta IC. That is this delta IC I can find out. And if I know delta IC, then I can find out Vout1 and Vout2 also. So Vout1 would be, I mean, the change in Vout1, that is delta Vout1. So the change in Vout1 is minus delta ICRC. Okay. Similarly, change in Vout2 is delta Vout2, which is delta IC times RC plus delta RC. Okay. So the overall differential output, the change in differential output, that is delta Vout, is delta Vout1 minus delta Vout2. Okay. So which is equal to delta IC times delta RC. Okay. Now one can find out this delta Vout by delta VCM, which is also common mode gain. Okay. And this common mode gain, I would ideally want it to be 0. So let us see delta Vout by delta VCM. So delta Vout by delta VCM, I want to find, where delta Vout is minus delta ICRC, IC delta RC, okay, and divided by delta VCM. Okay. And delta IC we will take from here, which is delta VCM by 1 by GM plus 2 RE. Okay. So I'll write this is, so delta IC from here, that is delta VCM times delta RC by VCM delta multiplied by 1 by GM plus 2 REE. Okay. So this delta VCM is common, goes off, so we are left with delta RC by 1 by GM plus 2 RE. Okay. So that is the common mode gain that we have achieved is finite, it is not 0. Okay. If this tail current source was ideal, that is the impedance was infinite here, then this VCM, that is change in input, so this would not have any effect on the currents flowing through the collectors of these two transistors. Okay. So if this source was ideal, then a small change in VCM, that is common mode input, so that might not have any change in the collector currents flowing through Q1 and Q2, because in that case the collector current was set by this tail current. But in this case, where the tail current source itself is not ideal, it is associated with a finite resistance, a small change at the input will cause a small change in the currents of these two transistors, which will also cause a small change in the outputs of these two transistors. Okay. That is, outputs will not be same, and therefore the common mode gain, so this will not be 0. Okay. So that is, we are finding it some finite value. So instead of finding a common mode gain to be 0, we are finding some finite value, which is this one. So this is actually called common mode to differential mode conversion of gain, which is represented by this ACMDM. Okay. That is common mode to differential mode conversion of gain, ACMDM. So we want this to be 0. Okay. That is ACMDM, we want it to be 0 ideally, but it is not 0 because of this issue, finite tail impedance. Okay. So a similar undesirable effect, that is common mode to differential mode conversion of gain, can be observed in MOSFET based differential pair. Okay. So again, in this circuit we have simply replaced the BJTs by MOSFETs. Okay. Rest of the circuit is exactly same, that is you have a finite tail impedance associated here also, okay, and a small change in drain resistance of this transistor. Okay. So one can again write delta VCM similar to what we had written for the BJT. Delta VCM is delta VGS plus 2 times delta ID RSS. Okay. So delta ID this time flows. Okay. I mean delta ID this is the small change in current due to small change in VCM by delta V. So this causes the change in current delta ID in both these two transistors. Okay. So this will also result into uh, a small change in the outputs, that is delta V out 1 and delta V out 2. Okay. So from here I can find out delta ID similar to we had found delta IC for BJT based differential amplifier. Now if I have delta ID, I can find out delta V out 1, that is change in V out 1, okay, which will be delta ID times RD. Similarly delta V out, change in V out 2, this is minus delta ID times RD plus delta RD. Then differential output, okay, that is change in differential output, so which is V out 1 minus V out 2, or delta V out 1 minus delta V out 2 in this case, which is equal to minus delta ID times delta RD. And then I can find out the gain, which is again common mode gain, okay, as delta V out differential output by the common mode input, change in differential output by the small change in the common mode input. Okay. And delta V out is this much, delta ID by RD. So you divide by delta VCM. So this will be the gain, common mode gain. Okay. And delta ID I'll take from here again, which has VCM. So this VCM will be cancelled with this VCM. So I'm left with this relation for the common mode gain. Okay. Now again, similar to the BJT counterpart, here also we notice that this common mode gain is not zero. Okay. It is finite. It is finite because of this non-ideal current source, or because of this finite impedance associated with the tail current source. Okay. So we wanted this to be zero. It is not zero. So it is not zero. It is undesirable that it is not zero. Okay. So this is again called common mode to differential mode conversion of gain, or represented by ACMDM. Okay. So we want this gain to be either zero or very small. Okay. Okay. If it is zero, so that means any noise which is common to both the inputs, so that will not be reflected in the output. Okay. The common mode gain, which is zero, so this also represents that if any noise is common to both these two inputs, so that noise will not be reflected in the output. Okay. Okay. Yeah. So we are interested in making this, I mean we want this term, that is common mode to differential mode conversion of gain, to be zero, okay, so that my CMRR can be very large or infinite. So for large or infinite CMRR, I want the common mode to differential mode conversion to be zero, or common mode noise should be equal to zero. Okay. But so that in this case, if some noise is present common to these two signals, so that noise can be rejected But here this noise will not be rejected because I have some finite common mode to differential mode gain. Okay, so because of this, the common mode noise appears in the output. The common mode noise appears at the output. So if CMRR is high, if it is infinite, that means there is zero common mode to differential mode conversion of gain. Okay, so that means no noise is present in the output. Now in some applications, one would like to have a single-ended output. Okay, so one would also like to have a conversion from differential output to single-ended output. So for example, here in this differential amplifier, if somebody tries to take the output only from this node, okay, and by taking it from this node, I say that this is now single-ended output. Okay, so this is a wrong approach. I mean, it's not very good approach to take single-ended output directly from the differential amplifier or differential stage, because the purpose of the differential output is to reject any noise coming from VCC as a ripple also, okay, and any noise which is common to these two inputs, so that will also be rejected. So that is actually the purpose of taking differential output. Okay. So if somebody tries to take single-ended output, so then that would be obviously meaning that, I mean, that would obviously mean that the output will contain noise. Okay. So noise will be present in the output. So no noise cancellation if I take single-ended output from the differential pair. So that is why this topology is not very good. Okay. So that is, this output will be corrupted by noise from the supply. That is, ripples from the supply will be present in the output. Okay. And also there is another problem, and that problem is that this differential pair is extracting two currents. Okay. Now this output is through one current only, so that is, this current is lost. I mean, it is not considered at the output. Okay. So that means half of the signal is lost, and also common mode cancellation is not present. Okay. So no common mode cancellation mechanism exists. So these are a few drawbacks of taking single-ended output from the differential pair. So in fact, there is a better alternative way to take a single-ended output from the differential pair. That is by considering a current mirror as a load to this differential pair. So Q1 and Q2 transistors, so they represent a differential pair. Now the load to this differential pair is a PNP current mirror, right? So this is my PNP type current mirror using only PNP type BJTs. Okay. So how this is better, let us try to understand here, or maybe yeah. So here you will find that there is no loss of gain, okay, because both the currents are evaluated at the output. Okay, that is, Q1 and Q2 both are responding to the change in inputs. Okay. So the current which is present, I mean, the current which is drawn by this Q1, so that is also used as a reference current for this current mirror. So this current is copied at Q4. Okay. And apart from the current at Q4 which is copied from here, Q2 is also generating a current in response to change in V in 2. Okay. So there is no loss of gain, and hence this is a better alternative. So this current mirror, so this is also called active load. Okay. So this is also called active load, and in this current mirror load, the signal current which is produced by Q1 here, so this is copied at Q4. Okay. So signal current which is produced by Q1, so this is copied or replicated onto Q4, and this active load is different from static load. Okay. So current mirror is a active load. Let me show you the static load also, maybe here. Yeah. So this is my active load, current mirror, and these two MOSFETs, that is Q4 and maybe this is Q3, let us call. So this is a static load. Okay. So when it is active load, so that would mean that my uh, this active load in the circuit, so this responds to any change in the input signal. Okay. That is, if it is active load, so then this load will respond to any change in the input signal. Okay. And if it is a static load, so this load will not respond to any change in the input signal. Okay. So any change in the input signal will cause the currents also to change. Okay. That is, if I say that, let us say that the input signal changes by delta V, that is, it increases or rises by delta V on Q1, and it falls by delta V on transistor Q2. Okay. So this is my change in the input signal. So my load should respond to this change in the input signal if it has to be active. Okay. So since this is an active load, the currents on Q1 and Q2 will also change by the same amount. So that amount is, let us say, delta I. Okay. Though I am using ideal current source, and ideally when I am using ideal current source, the collector current should not change for a small change in input signal. But since I am using a current mirror which is an active load which responds to any change in the input signal, so therefore for this change in the input signal, that is delta V on both sides, the current in the Q1 and Q2 transistors, so they will also increase and decrease by the same amount delta I. Okay. Now because I am using a current mirror over here, so this current, that is IEE by 2 plus delta I, so this will be used by this current source as reference current at this point, and this reference current, that is IE by 2 plus delta I, will be copied on Q4. So that is IC4 will be equal to IE by 2 plus delta I. Okay. And because of the change in the input at Q2, the current at the collector of Q2, so this also changes by delta I amount. So that is, current in Q2 is IE by 2 minus delta I, and the current present here IC4, so this is equal to IE by 2 plus delta I because of the current mirror action. Okay. So that means total current that will go into this load resistor, so that will be 2 delta I. Okay. Now the role of this differential pair, we are saying that it is trying to decrease the current which can go into RL by delta I amount, but then current mirror circuit at the load, so this is pushing extra delta I into this RL, delta RL. Okay. So this actually enhances my output. Okay. So however, in the case of static load, any small change in the input will not affect the current on the collector of these two transistors. Okay. So that is, the differential output will be 0 in this case if V in 1 and V in 2 are same. So this load does not respond to any change in the input. Active load responds to the changes in the input. Okay. Now, similar to the BJT based differential pair with active load, one can also design a MOS differential pair with active load. So it's a PNP, not PNP, a P-type MOS or PMOS cascode. So PMOS cascode can be used as a load to a MOS differential pair. Okay. So again, same analysis that we had done for a BJT based, this kind of circuit, that is differential pair with active load. So same discussion applies here also. Okay. That is, the job of this current mirror is to enhance the single-ended output. The output is single-ended here across this RL. So the job of this current mirror is to react to any change in the input and to enhance the output. Okay. So with this, I think I'll stop here, and we'll carry on from here in the next lecture.